My name is John Rinaldi, and I'm with Real-Time Automation. I want to talk to you today about Modbus TCP. Ethernet in general and Modbus TCP in particular, there's a lot of confusion. Hopefully the few things I'm going to say here in the next five or 6 minutes are going to tell you what you need to know about Modbus TCP. Let's start with Ethernet. In an Ethernet packet, you have basically that travels. That's the lowest level. An Ethernet packet moves from one node on Ethernet to another node on Ethernet. Inside that packet, there's an IP layer. It's an IP header, and there's an IP trailer. And that essentially just says, I want to go from this place to this place. Within that packet, there's TCP header and a TCP trailer. And that's essentially the connection you have between two nodes. Now, a lot of people get confused right here. The data in this packet, a lot of devices just send raw data in that packet. And they'll just put in there an ASCII string, a barcode, a scale weight. But the key is that the receiver doesn't really know what's in that packet. He just has to have an implicit understanding of that this is a scale device. It's going to send me a weight, and it's going to send me a tare weight, and it's going to send me these three other parameters, and they're separated by commas, or they're in binary format. They're 16-bit binaries, 32-bit binaries, whatever. There's no good understanding between the two nodes about what is going to what's going to be sent and what's going to be received. So that's why you need a communications protocol, an application layer protocol, to go within this packet. One of the most common ones, the one we're going to talk about today, is called Modbus TCP. So what Modbus TCP does is define the contents of that packet so that the receiver can open it up, look at it, and figure out what this message is. In Modbus TCP, this message could be, I want to get some data from you. I want you to send me some data. I want to start a process. I want to terminate a process. It could be a million different things, but because of the implicit understanding between the two nodes that this is a Modbus TCP message, both sides, the sender knows what to send, the receiver knows how to interpret what's sent. So this is so that's the whole point of having an application layer protocol in there. Now let's talk about Modbus TCP in particular. The first thing that's really important about Modbus TCP is the data representation. In general, with any protocol, any industrial network, Modbus TCP, DeviceNet, OSI, it doesn't matter. You have to understand what the data representation is. How does the network organize the data? Now, in the Modbus world, not just Modbus TCP, but Modbus RTU, which is the 485 version of Modbus, data is represented as registers and coils. Registers are simply 16-bit unsigned data values. Coils are single bits. So every device on a network has some number of registers, has some number of bits. You can actually have 64K worth of registers and 64K worth of bits. Most devices don't have that many, but a device can have as many as it needs to have. So it may just have one register or one bit at the minimum. But so every message that goes back and forth in the Modbus TCP packet has once it performs some kind of action on the data in the device that's the receiver of that message. So it can either read that register or coil or write that register or coil. Now how it does that, this format is very well known and well understood. What you have is a function code, a address within the data representation, some kind of length, and some kind of data. It's a bit more complicated than that, but I'm going to simplify it for the purposes of today's simple overview. The function code says, I am reading registers, I'm writing registers, I'm reading coils, I'm writing coils, and there's different sets of registers and coils you can have. And this goes back to the old days when they actually had real analog inputs, and then you had inputs that were in memory and such and stuff like that. So function code There are some function codes to read input registers, other function codes to read holding registers. In today's devices that are more virtual devices that have just a bank of memory that you're accessing, we've kind of gotten away from that. But some devices use function code 3, some devices use function code 4. It all depends upon the developer of the device, what function code they wanted to use to access their data registers. Same thing for coils. There's input coils and there's status coils and output coils and stuff. The address is simply the offset into that register list or coil list. The length is the number of bits or the number of coils you want to read or write, and or the number of registers you want to read or write. And then there's the data. If you're writing data, you specify, here's the data I want to put into those devices. So it's a very, very simple kind of data representation format for this command message. That command message fits right into this TCP packet, so the receiver can open it up, looks at that function code, and says, "Hey, they want to read input registers, but I don't support input registers." So then he just sends back a message saying, "Well, here's an error code because I don't support that." Or he says, "Oh, they want to read holding registers. Oh, I've got holding registers." So then they look at the address and say, "Well, that address is outside the bounds. I'm only supporting addresses 100 to 200. They want to read address 300. Well, can't do that. So send back an error code." But if the address is in range, if the number of registers they want to read is still in range of data that's available, then the device will answer, put a message back in the TCP packet. So what this says is, the sender has to know what the data representation is for the device at the other end, and know what it has. Does it have registers or coils? How many of those does it have, and where are they located, so it knows how to form this message. So using this, two devices, a sender and a receiver, can make a connection, send Modbus TCP, Modbus commands back and forth over the TCP message, and when they do that, they'll be able to easily communicate and transfer data in a way that's very understandable. Now, Modbus RTU is the same kind of message structure. It's actually got an address on the front, a station ID on the front, because Modbus 480 RTU is on RS 485, so that's a multi-drop network, so you need a station ID to indicate which particular device. On Modbus TCP, we don't use that because we've got an IP address. We've made a connection with a specific IP address. On 485, you have to identify the station it's going to. So that's really the only difference between it. On Modbus TCP, Modbus RTU, we also have a CRC at the end. So to go from Modbus RTU to Modbus TCP, we take the station ID off, take the CRC off, and put it on Modbus TCP. Now there's also an additional field that's used for Modbus TCP. It's something called the unit ID, the UID field. So if you had that particular Modbus TCP device had some other set of devices that it was controlling, you could use the unit ID then to say, I want to go to this IP address, but when I get to this IP address, there's a number of units there. I want to talk to that particular unit. So real-time automation is an expert in Modbus TCP, among other Ethernet protocols. We have Modbus TCP source stacks for clients, which is the side that makes the connections. We have Modbus TCP stack for the server side, the one that accepts the connections and represents the data. Really, it's all strictly ANSI-C. It's TCP stack independent. It's RTOS stack independent. Works on any processor with any size. So give us a call. Go to our contact page on our website, and we'll be glad to talk to you about how we can get you connected on Modbus TCP.